Hey everyone, we are looking at a classic application of integrals, and that application is area between curves. So we're going to start ourselves off here. We're going to find the area of that triangular region, that's in quotes because it's not technically a triangle because of curved things, but whatever. So the triangular region in quadrant 1 that is bounded by the graphs of y equals 4 minus x squared and y equals x minus x squared and the y-axis. Now, a lot of the times you're not given a graph, or even if you are given a graph, you're not told the region, you just are described the region. So when you look at this, there's a few regions that your eye goes to. There's like this guy right here, there's this guy here, and then there's that weird lumpy bit on the side. Well, this bit's clearly not a triangle, so that's out. Looking at the other part, well, only one of those is bounded by the y-axis. So it's this region here on the left that we're looking at. So first of all, just getting an estimate, that's not a bad idea because it tells if your answers are going to be like reasonable. Well, if this is a triangle, its height is 4, its width is 1, and base times width divided by 2. So this area is about 2. So that's a good thing to pay attention to. So that counting of boxes that we did way back when, or looking at it like that, or just kind of eyeballing it, it's a good idea. Okay. Now, this is something that's going to come back repeatedly, especially when we hit our next application. And so having a feel of it now is going to really help you out. Okay, remember way back when we did those Riemann sums? So like I could fill this region up with rectangles. I'm only going to draw one rectangle. So I'm just going to draw this long, skinny strip. So this is what is known as a sample rectangle. The height of it is going from the blue to the red, which is the 4 minus x squared and the 4x minus x squared. The width of it is just this little skinny change. It's a little tiny width of x. That width ends up being called the dx because it's just some small change in x. I know I could fill this guy up. I could use my Riemann sum program and find it, but we're going to actually find it exactly using calculus. So now the height of this rectangle is, like looking at this particular one, it's about, say, 1.5 for on the bottom, and the top is at about 3.7. I can find this height by doing 3.7 minus 1.5. Of course, this is a sample rectangle representing all the rectangles that fills this thing up. So no matter what, though, the height of this rectangle would be the blue minus the red. Top minus bottom. So when we consider this what we call a sample rectangle, we know a rectangle is just base times height. So basically we're saying height times, not weight, that's ridiculous, height times width. So it's just those two dimensions. So the height of this guy is the top minus the bottom, which means I'm talking about y values. And the width of it is, in this case, dx. By the way, our width, we'll see our next example, our width will be dy. So the skinny dimension of your rectangle is always a dx or a dy. If you ever have something else for your skinny dimension, you probably messed up. Okay, so my top, I'm gonna label some things just because it makes life easier. I'm gonna say let y1 be 4 minus x squared, the blue guy. And I can even label that on my drawing. And then let y2 be 4x minus x squared. If I'm using my calculator, I make my y1 and my y2 correspond with what I've put in my calculator. I have a color calculator, so I can even match my colors. It's pretty handy. So then this red guy is my y2. So if we're doing top minus bottom, blue minus red, apologize if you are colorblind. So it's going to be, and I apologize for the amount of clicking I'm going to be doing in part of this video because I'm going to be switching colors. So I have y1 minus y2 for the height of my rectangle, times my width of dx. So this is my sample rectangle. I did not plan my spacing well. So what I will call this is d A, as in it is some little change in area. It's a little strip of area. To find the whole region, I will add those rectangles up. Remember those Riemann sums? So if we're going to sum these guys, oh wait, you know what else is a sum? An integral. The reason an integral sign looks like an S is because it is one. We're saying we're going to get all the area, so basically this guy is A, by integrating the y1 minus the y2. And we need some bounds. I'll come back to that in a second, but let me first get my y1 in here. And by the way, this dx is the boss. So you never are going to be mixing x's and y's. So this dx is telling me, rather than saying y1, it really is 4 minus x squared. And then my y2 is really 4x minus x squared. So there's my top minus my bottom by replacing those. I'll clean that up in a moment. And my dx. So now my bounds. Well, the left bound is 0, and the x is in charge. So my x is, so this dx is in charge saying, look at the x values for what my bounds are. So the left edge is 0. The right edge is 1. You can find that right edge by 1 if you have your thing graphed and you find the intersection. You can also solve it algebraically. You know, things like saying 4x minus x squared equals 4 minus x squared, which means 4x equals 4 and x equals 1. So there are my bounds that way. So I can solve it algebraically. I can solve it graphically. I can use my calculator. So multiple ways to get there. So my bounds are 0 and 1. So now to integrate this, before I integrate, I could integrate this as it is, but why should I integrate a complicated thing? I'd rather integrate a less complicated thing. In other words, I'm going to clean this guy up. So I have my 4, negative x squared minus negative x squared, that's gone. Oh, that's convenient. And then I have my minus 4x. So be really careful with your pluses and minuses. If you need to write another line where you distribute this negative through, you can do that. Just watch those pluses and minuses really carefully. Okay, so from here, I'm going to integrate it. So my area is going to be 4x minus 2x squared from 0 to 1. And then I can plug in my 1. So I have 4 times 1 minus 2 times 1 squared. Okay, I know plugging 0 in gives me 0, but just as a reminder what we're doing here, I am plugging that lower bound in. And remember, just because if one of your bounds is 0, it doesn't guarantee that the answer is 0, because like e to the 0, for example, is 1. So just watch that closely. So no matter how you slice it, we get 4 minus 2. Hey, that's 2. That fits the estimate. It's almost like I'm good at this or something. So there's our area. So the exact perfectly 100% correct area here is 2. Now I can do this on my calculator as well. Like here's the same graph, and I'd still have my y1 is the blue and the y2 is the red. I kept my order the same just because it's easier that way. And then remember, I can go math 9, 0, and 1. And then I can do y1, so that alpha trace, minus y2 and my x. So this is a nice way to check an answer, but if you're asked to solve something algebraically means solving it calculusly, as in doing all this stuff here, versus if you were asked to solve it numerically, that's oddly enough calculatorly. So if I do that, it thinks for a moment and it spits out the 2. So your calculator can do this too. So it's really, really a nice way to have it in both directions. By the way, if you mess up your order, like if I accidentally did y1 minus y2, but it should have been y2 minus y1, the only thing that would have been wrong is negative. It would have said negative 2. And obviously I know an area is not negative, so I would just be like, oh, I'm just going to pretend to put it in my calculator right, and I'll fix it on my paper, and I will get the right answer. So it's just straightforward. So it's nice that you can check answers using your calculator. Okay, so this is our first example. We will have a second and third example as well.